Hey everyone, welcome back, and today let's solve Leetcode problem 115 titled Distinct Subsequences. So we're given two strings s and t, and we need to return the number of distinct subsequences of s which equals t. And the test cases are generated so that the answer fits on a 32-bit signed integer, which is pretty good. We know that our integer is not going to overflow. So in example 1, we have our input string s and t to be rabbit and rabbit following, right? The only difference is that s has an extra b, and we output 3. Why? Because as shown below, there's actually 3 different ways or subsequences we can generate rabbit from s to equal t, right? There's 3 different subsequences present in s to equal rabbit in t, right? We have rabbit, we have rabbit, we have rabbit, right? We're just simply using different b's from the group of 3 b's that we have, an extra b in our input string s. In example 2, we have our input string s to be the following, and we have t to be bag, and we output 5. Why? Because there's 5 subsequences in s that are equal to t. We have bag, we have bag, we have bag, we have bag, we have bag. Okay? We're just simply keeping the relative order of our indices of our elements that we're using. That's how a subsequence is defined to be. We're simply just grabbing different elements from our input string s and checking if they can form a valid subsequence that's equal to our input string t. So with that out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution. And then I'll show you guys how I would optimally solve this problem in a few seconds. So honestly, when you see subsequences problems on Leetcode, your mind should kind of directly jump to dynamic programming, because 99% of the time when you have or trying to solve a subsequence problem, it is most likely going to be a dynamic programming solution, which is exactly the algorithm that we're going to be using for this problem. And it's, again, well suited for all these subproblems that overlap, is because we need to actually compute combinations of different substrings that we can form, or subsequences that we can form efficiently. So the way we're going to structure our solution, we're going to actually have a 2D array. I'm just going to call it dp, where dp at any index I and index j is going to represent the number of distinct ways to match the substring of t from up until index 0 up until index j with the substring s from index 0 up until I, right? And we're also going to create a kind of base case scenario, right? So when j is equal to 0, basically meaning when the target string t is empty, there's only going to be exactly one way to actually match any prefix of s with an empty t. What is that? It's simply by deleting all of its characters. And if I isn't equal to 0 and j is not equal to 0, it's greater than 0, then there's no way at all to form t from index 0 up until index j from an empty string s. It's simply impossible. There's no subsequence of s if it's empty to form t. Okay, and so we're going to use 2 nested loops to actually populate our dp array that we define. And for each character in our s and t inputs, we're going to update dp at index I index j based on whether the characters match. So if s at index I minus 1 is equal to t at index j minus 1, we can kind of extend that or update dp at index ij to be dp at index I minus 1 j minus 1 plus dp at index I minus 1j. Otherwise, if that's not the case, if those 2 previous characters are not equal, we have to set dp at index I index j to be equal to dp at index I minus 1j. Right? So with that out of the way, let's just go ahead and dive straight into code here, and I'm kind of going to explain that a little bit better to really understand how this actually works. Okay, so I'm going to quickly have m and l, like I usually do for dynamic programming problems, to be equal to the length of our input string s and the length of our second input string t. Right? These are just going to kind of help us know the bounds and dimensions of our DP array for easy access later when we define that data structure and kind of access them with our nested loops. So now, quick kind of base case here. If n, the length of input string t, if that's greater than m, there's no need to even actually instantiate or check our DP code. We immediately know that if the length of t is greater than the length of s, it is impossible to find t as a subsequence of s, because there's not even any characters or enough characters to actually use to form a subsequence, and so we can immediately return 0. There's 0 ways to do that if the length of t is greater than the length of s. Now, once we do that, now we can actually kind of build or initialize our DP array with its corresponding dimensions. So in Python, it's pretty straightforward. We'll set DP equal to an array of 0, right? It's going to be filled with zeros times n plus 1. and this is all going to be in the range. I'll just use an underscore for my iterator, because I don't really need to use it here. In the range of m plus 1, right? It's simply going to have dimensions of m and n, right? Where m and n are the lengths of our input string s and t, right? And again, it's going to be filled with zeros, again with dimensions m plus 1 by n by 1, where each entry at dpij is going to store the count of ways to actually match t starting from index 0 up until j with s starting from index 0 up until I, okay? So now that we've initialized this DP array, now let's actually scan through and populate it, or rather begin populating it. So for I, in the range of m plus 1, right? Again, note that m is the length of our input string s that we're trying to find subsequences for. We want to set dp at I, comma 0 to be equal to 1. Why is it equal to 1? We have to just initialize this first column, right? That's why it's I, comma 0. We're initializing that first column of this DP array. And for any substring of S, there's always going to be exactly one way to match it with an empty T, with an empty string T. It's simply by deleting all the characters. And so for every single element in the first column, it's going to be initialized to exactly one way. 1, the value of 1 in the first column. When this simply covers cases when we have an empty string T, right? There's only one way to match it, an empty subsequence. Now we have to do the same thing with the nested loops. So for I and the range starting from 1 up until m plus 1, right? M plus 1 exclusive, because that's how for loops work. And for j in range of 1 up until n plus 1 exclusive, or n inclusive, right? Simply just iterating through all the different characters of s, where we use index I and t, right? To basically just help us fill out our DP table by simply checking all of the substrings of s and t. Okay, so once we do that, now we have to have our first conditional. The first conditional, like we talked about before, is if s at index I minus 1 is equal to t at index j minus 1. If that's the case for these previous two characters, we can update or extend our dp at index I, comma j for this subsequence to be equal to dp at I minus 1j, or rather I minus 1j minus 1, sorry about that. That's how I'm going to structure this, plus dp at I minus 1j. Again, addition is commutative for any of you guys who are good with math, so I could have structured this or reversed the order of the way I'm adding it. It doesn't really matter. It's going to yield the same output. But why are we doing this? Well, if s at I minus 1 matches t at j minus 1, then we have to actually add these two values. What do they mean? Well, dp at I minus 1, j minus 1 is going to represent the ways to match t starting from index 0 up until j minus 1 with s starting from index 0, I minus 1. If we consider s at I minus 1 as part of that match in the subsequence. And dp at I minus 1j, the extra value that we're adding here to that value, is going to represent the number of ways, different ways again, to match t at index 0 up until j without using s at index I minus 1. But if that's not the case, so else, if we fall in this conditional, we have to just simply set dp at ij to be the same value as dp at I minus 1j, right? Pretty self-explanatory here. Why are we doing that? If s at I minus 1 and t at j minus 1 don't actually match, then the count of ways to match t from index 0 up until index j remains the same as for s at index 0 up until I minus 1 without actually using s at index I minus 1. And so we have to just manually update or set our dp at ij to be equal to dp at I minus 1j. And effectively outside of this nested for loop, once we're done iterating through all of these different characters I and j and our input string s and t, we simply have to return dp at m comma n, where again m comma n are kind of our boundary points, the lengths of our input string s and t. Right, and that's going to contain the number of ways to actually match t from index 0 up until n with s from index 0 up until m, right, which is exactly what we want from the beginning to the end of the corresponding arrays, or rather strings, right? And unless I made any syntax errors here, this should be accepted. And as you can see, this is just about as efficient as you can get. So to kind of reiterate, what does this code do overall? A quick high-level explanation. We're simply using dynamic programming to count the distinct subsequences of S that actually can be formed to be equal to T, our second input, right? And our DP array is going to help us store intermediate results, essentially avoiding redundant calculations and ensuring our efficient processing. And for each character comparison, we have to consider both matching and our non-matching cases and accumulate all the different ways on subproblems to achieve the match of index I-1 and J-1. So for the time complexity of this solution, this is going to be a big O of m times n solution, where again m is the length of our input string s and n is the length of our input string t, respectively, because really we're filling out that DP table of size n plus 1 by n plus 1, and in a nested loop, we have to actually iterate through all the different arrays, or rather elements in our input string s and t, and that's going to be a number of big O of m times n operations, because really we're checking every single element exactly once. And for our space complexity, this is also going to be big O of m times n for that extra auxiliary memory that we use for that 2D DP table that actually stores the results for each substring or subsequence combination for every single index I, comma j in our DP table, right? It's going to have the same space as m times n because that's the dimensions of that 2D DP table. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.